Zeynep. Today I will be your math instructor and will try to explain you a fundamental theorem of integrals and try to dive deeper in this topic. So let's start. First of all, yesterday we learned about integrals and finding the area under the curve. What we have learned was the geometrical part, the easy and boring part, because if you take a look, for example, if you write here f of, for example, 2x dx, what we did, we just plugged instead of x numbers and draw the line. So if we, for example, plug in numbers 0, then for example 1, 2, 3, we will get numbers and this line. So as we draw this line, we have basically the sides of triangle, and it's easy to find its area by geometry, by formulas, because we know as a multiplied by b divided by 2, so it's the easy part. But what if we have something more complex? For example, curvature. Because here, as we see, it's the curvature. We don't have such a shape. We didn't cover any formulas, geometrical formulas to find the area of the shape. That's why now we will connect this part with integration and with derivatives. It will be very interesting. I hope you will like it. So let's start, first of all, with the notation of area under the curve. For example, we have such a curve, and we want to draw borders here and here. We cannot take these borders as a and b, x values. So what we have learned basically how to show this was with integrals dA f of x dx. But as we know, the letter for area in geometry is a, and if you want to show it like for integrals, for example for example in geometry, what we did, a equals, for example, of square, a squared. For example, for triangles is ab divided by 2. But to show this for the curve, we can write it as a as a function, a of x. But to know whether this x, for example, is it a, is it b, is it 2, what should we write? We should know that this parenthesis shows from which starting point does it go. So the starting point and the end point of this shape. For example, if I write here, for example, a as a function of a, so it depends from a, it means that it starts at a and ends at a. But for example, a of x, so x is going to, we don't know where does it go. You can write it like this. And if we plug in some value instead of this swallow-shadasi, we will get that the figure, the shape is going from A to something. If I plug in A of A, it means that it goes from A to A. So the area will be 0 because there is no such a shape under the curve from A to A. It's just like rectangle, just a side of rectangle. There is no area, it's just a line. Yes?
Could you please explain that part again?
So basically, I want to explain the notation. How we can show the curvature with a, for example, a of x as a function. And for example, when we plug here some value, x value, we want to know which x value should we plug in here to show the shape, figure under the curve. And for example, we have such a thing that if we plug in here something, it means that it goes from this point, for example, we can determine this point, to the final point. If I write here, for example, a of a, it means that it goes from a to a, you see? And from a to a, there is not a shape, it's not a figure. From a to a, this area is just a 0. Yeah. But if I write p, so it means from a to b. So it shows that the figure is going from a to b. So it shows the shape under the curve.
So our a function is the definite integral.
Yes, so we can show this notate as this, a of b. Or for example,
so a of x equals to that function at the top.
Yes. there is another example. For example, if we have here z and y, how I can notate it here? How do you think?
AY.
Yes,
Because
exactly.
it's going towards the
Yes, it shows that.
Y border.
Yes, it shows that it starts from here and ends at y. It basically shows the end point. From where to where does it go? I hope everyone. Yes, ma'am.
Can you give an example with numbers?
Yes, of course. So, if we have another curve, for example, like this, and want to show the figure under this curve. It's 1 and it is 4, for example. To show this, how do you think? What should we write?
4.
Yes, exactly. It will be the right
Why A
notation.
is always 1?
What?
Is A is
No,
always
we can-
first term?
No, it's not always 1. We can just show it with the integral. We can just plug in any number here. If you want, for example, find the area, this area. For example, we want to find the figure of such shape. We can write here anything we want. -1, or if we want to find the figure of this, 1, 2, we can determine what do we want to find.
Okay.
And so basically we should always write the end point, show the notation.
Okay.
Our goal is to find area of one rectangle, because as we know, to find the area we should find area of one rectangle and then sum it all up. But we know there are infinitely many rectangles, and to find this we can take, for example, one rectangle here and notate it as written here, for example, from A, B, and X. And to show, for example, the area of this, we can notate it as A of X. Yes. So it shows basically the area of from A to X. And then to show the rectangle, we can write it. If we want, for example, go a bit to the right or to the left, we can write, for example, X plus something. And this something we can notate as H. For example, in the definition of derivative, we also use H to show the change, for example, from X. So here was X, it was X plus H. H basically shows the change from X to something. It's just some number. We don't know which number, we just assume it. So if it is X and this is X plus H, so this distance is H, as we see here. And if it is X, let's draw it bigger size to show how does it work. For example, as we see here, that the rectangle doesn't perfectly fit under the curve. And there is always a gap between the curve and the rectangle. This gap doesn't allow us to find the exact area. And to find the exact area, we should try to minimize this gap. So if there is X plus H, we should try to minimize this H. So basically, we want H approach to 0. We want H to be smaller and smaller. For example, if H here is, for example, 2, we see that there is a bigger gap. If we draw, for example, H from here, we see a gap. It is much smaller than here, so H will be smaller, and we try to minimize this H to the 0 to get as small gap as we can get. Yes.
Is it the same as the thing that Ms. Shams taught us with differentiation, when we have to get the smallest distance?
Yes.
To get
Basically, it's the same concept. We should try to get the most precise rectangle, so we should minimize this gap by decreasing the H, because as H decreases, the gap also decreases. So from here, we can already see the property of limits, because what limits show us? That something approaches to something. And here we can see that if it is X plus H, we can write that, we can also understand that H approaches to 0. But, okay, we understood this part, but what to do? Okay, we find width, if it's H. But to find the length, or we should find the area of this rectangle, I want to draw it in a bigger size to show it more precisely, because it's a bit messed up.
Don't touch forward.
So, Mr. David,
Yes.
so you're saying that as the rectangles get smaller, our area approximation gets better.
Yes,
Because
because yes, you can say because H decreases, and gap between the curvature and rectangle also decreases. Look, for example, here. We see that, for example, if it is our h, you see, the gap is much bigger. You see the gap, and if we decrease the h, if we will take, for example, h a bit smaller, like rectangle will be smaller, then this is the gap. We see the difference from this rectangle that we just drew, and this. So basically, h should approach 0 to make this rectangle more precise and find accurately the area. Okay.
So that's why you're saying we should use it.
Yes.
You're gonna
Here we can see the property of limits.
Oh.
But another point is that, okay, we find out about h, but we want to find, as I said, our goal to find the area of rectangle, because our mission is, we know that, okay, the curvature consists of infinitely many rectangles. And we know that the area is just sum of all these little rectangles. And our goal is to find an area, to find the formula, how to find the area of one rectangle, so we can sum it up. So let's take a closer look to this rectangle. I will draw it a bit bigger, just to make sure we see it. So what we see here, if it is x, this is x plus h. So what will be this curve? It's basically f of x. We can write it here, f of x, because f of x just shows the height, y. And to show this curve, what can we write here? How do you see it? Yes, it is f of x plus h. But yes, as we see, f of x plus h, it is here, and f of x is here. But the rectangle doesn't fit, so it's just not the height of the rectangle. We see that f of x plus h is too high, f of x is too low. So the height of rectangle is basically between f of x and f of x plus h. And we can denote this as, for example, y we can denote it as y to find this, so height. And if we show that the height of this rectangle is y, for example, in the picture, you can see it more clearly. As you see here, it is the curvature, f of x plus h, it is f of x. So f of x and f of x plus h is basically where x and curvature, they have, so the figure, the intersection for in the curvature. But the rectangle doesn't perfect, so it doesn't fit f of x plus h and f of x. So what we can do here, that to find the area, for example, of this part with f of x plus h, we can write it as a of x plus h. Because, okay, to find the area of this rectangle, what should we do? We should subtract f of x plus h area from f of x, because it is the whole f of x plus h, and if we subtract from this f of x, we will get this rectangle in the middle. So basically we can write f a of x, and it will be equal, and as I said that if we denote the height of the rectangle as some y, and if the width is h, because x and x plus h is h, and it's y, we can show that the area of rectangle will be logically this length multiplied by width. So it will be y multiplied by h. And from here we can already see that there is something similar to a definition of derivatives. Because if we will divide both sides by h, we will get a x plus h minus a x divided by h equals y. And perfectly we got here the definition of limits. And as you see, I hope everyone understood this part. If someone didn't understand, I can explain one more time.
So you're saying that left part of the equation looks very much like the definition of the derivative,
Yes.
right? Yeah.
Because y is the length of this rectangle, h is the width. So to show the area of this rectangle between, we should subtract this area from f of x. So basically the whole area we subtract from f of x, and we left only this rectangle area. And rectangle area, as I said, that f of x plus h and f of x, they doesn't perfectly fit the height of this rectangle. That's why I can show this height as y or another, for example, letter. And the width is h. So basically the area of this rectangle is height multiplied by width, y by h, as I wrote here. And it's basically equals to the subtraction of area of whole this curvature function from the f of x. So I hope everyone understood this part. And from here, as I say, to minimize the gap, we should try to we should make h approach to 0, because as I told, if h decreases, so the gap also decreases. We should minimize the space between rectangle and the curvature. So that's why here we can use the property of limits and write that limit as h approach to 0. So we just should copy this h equals, and y, well, I want to ask, for example, someone, as we decrease the h, what will be the y? To which function does it go, approach? For example, I decrease the h.
X function.
fx, just
Yes.
fx, not
Yes.
h.
Exactly. It goes to fx, because as we decrease h, it goes closer and closer to the f of x, and so it will be, we can denote it as h approach to 0. As it decreases, it will become f of x. And from here, we can see that it's just a derivative formula, definition of derivatives, and we can write it as a x equals f of x. Do you understand this part? How we get a derivative of x equals f of x?
Yeah, we're just taking the limit as the h approaches to 0.
Yes.
Why do we make the h approach to 0?
We want to minimize the gap between the curvature and the rectangle. As the h approaches to 0, the gap decreases, because as you see here, the gap, so as, for example, if h, length of h here, for example 4, the gap will be much bigger. If we decrease h, the gap is getting smaller, 3. If you decrease, it gets even smaller. That's why we should try to make it approach to 0, so the gap decreases maximum.
So,
we
we
should
can
get-
approximate this.
Yes, exactly. So we just can write it as a limit h approach to 0, and here we got this formula, a derivative of x equals f of x. And the interesting part that we can integrate both parts, and we will get, as we integrate the derivative, we will get a of x plus c, and here we will get f of x plus c. And we know that c, they are just numbers, so we can write it as 1c. If we take c from the left to the right, we will get f of x c minus c. And as we learned that sum of c, so if we plus, if we minus, multiply, divide, it doesn't matter, it always will be c. So we can write c minus c as just 1c, so it will be just a of x equals f of x plus c.
Okay.
Yes, do you understand? And now, as I say, c is undefined. We don't know what is c, because we cannot just write in the formula a of x equals f of x plus c. So we should find this c. And to find this c, I want to draw this function one more time, but clearly to show you where does this shape starts and ends. So you can see the formula in this function under the curve. Show the formula. And here we can write, as I said, if x will be a, what will be the area? So if I write, for example, a of a, what's the area of this?
0.
Yes, exactly. So if I plug instead of x, a, it will be a equals f of a plus c. And as I told you that a of a is 0, it will be just 0 equals f of a plus c. And from here we can see that c equals, we just send it to the left side, it will be minus f of a equals c. So we understood that c equals minus f of a.
Okay.
Yes?
Yes, makes total
F of
sense.
x is antiderivative.
Yes. F of x is just antiderivative of this f of x that I draw here. I can draw it one more time. So it is x, it is x plus h. So this is f of x, and this is f of x plus h. So big f of x is the just antiderivative of this f of x. So we got that C is minus f of A, and if we go back and plug in instead of C minus f of A, we will get the formula A of x equals f of x minus f of A. And now we can plug in instead of xb, because as I told you, to find the area, to define the area, we should take the endpoint. And here our endpoint is P, so we should substitute instead of xb to show this area. So we write A of B equals f of B minus f of A. So basically it's our formula that we just proved derived from this function. I know it's a bit complex, but it's really easy to understand because it just makes sense how we got from this rectangle this formula. So it's the formula that we got, yes, AB equals FB minus FA. So basically, yes, the area of this so this figure is the integral of B, f of B minus f of A. So this is our formula. I hope everyone understood how we got this. If anyone has questions, yes.
And why did you equate to 0, f of A plus c?
This, because
A of A.
as I wrote here, A of x equals f of x plus c, and in the beginning of at the beginning of lesson, I told you that if, for example, if you plug in instead of xa, what will be the area of A of A?
Ah, 0.
Yes, exactly, because it shows that it starts at A and ends at A. So there is not basically no shape under the curvature, so it will be 0. And we plug instead of xa, AA, so it will be 0 equals f of A plus c. And so we send f of A to the left side, it will be c equals minus f of A. Then we just plug in instead of c the minus f of A that we got here, and then we plug instead of x b to show the whole this figure that is under the curve.
So that's the formula for area of a square under the curve.
So yes, figure under the curvature, yes. It's our formula. And now we can see better, for example, in this form. If you want, you can take a picture.
Okay.
It's basically what I explained, but in a bit proper way. So yes, I hope everyone understood this theory as I explained. And now I think the best thing after the theory is just practice it. I will just show you one example that I will do myself. So then I will give you examples and you will do them so at the board, and we will see 3, 0. Then for example we can take 2, or for example 4 dx, or okay, for example 2x. So we have this, so this is our integral, and we want to find the area for this function, for this integral. So as I wrote here how to find it, first of all we should integrate this 2x. So as we integrate 2x, we will get x squared. C we didn't write because as I told you that we don't need C, as we already showed this in this proof. So basically we can write x squared as I told you, but instead of x we will plug first of all b at the top of this. So I'll write b squared minus, we'll plug now instead of x a, so it will be a squared. So we got here such an equation, and now as we know that b is on the top and a is on the bottom, we should just plug in instead of b 3 and instead of a 0. And as I plug in here 3 squared minus 0 squared, we'll get 9 minus 0. So our answer is 9. So basically this is how we found the area under this curvature.